Okay, so now let's talk about energy economics. So there are many ways for us to calculate the viability of a certain project, especially related to distributed generation in our context. So we need to take into consideration, for example, the capital cost of equipment and operation and maintenance cost. And all of this must be considered together when we perform financial analysis. Okay, so the examples that will be shared in these slides are obtained from a textbook, and some of the examples are ideal in the sense that it does not represent the complication or complexity of actual financial analysis, but it provides a good fundamental knowledge on how to determine the economic viability of a project, how to do financial evaluation, and whether to embark in a more detailed analysis of the project. Okay, so let's look at the concepts. Okay, these are the basic concepts that you need to know. Okay, first one is simple payback period. Now, simple payback period is commonly used for us to evaluate the time required for our investment to uh, to to be returned back to us, right? In terms of cost. Okay, so the equation is straightforward. It's the division between what the total amount of money we need to spend divide by the annual savings. Okay, so very simple. So simple for us to understand, but the disadvantage is that it can be misleading in the sense that it can show as if the investment is worse than what it actually is. So for example, if you buy an air conditioning that costs an extra 1,000 but can save 200 per year in electricity bill. So we simply divide the extra cost with the total saving per year. So we get 1,000 divided by 200 per year, so 5 years. So simple payback states that uh, the payback period will take us around 5 years if we spend 1,000 now. So maybe for us, if it takes 5 years just to get back 1,000, maybe many of us say it's too long, right? Okay, but later when we represent the case as internal rate of return, like the sentence here, then you might be able to twist it a bit to make it more interesting or more appealing. Okay, but save the case for now. We just go to the simple example here. Simple payback period is not so attractive. So there's another inverse way of saying it, the simple payback period, or stating the simple payback period. We call it as simple rate of return. And we obtain this by simply finding the inverse value of simple payback period. So 1 divided by the simple payback period. Okay, so opposite from the simple payback period, the simple rate of return may make the investment sound too good than it actually is, right? So if we divide 1 divided by the simple payback period just now, so for example 5 years, so 1 divided by 5, we get 20%. So 20% annual return sounds good, but if the device cannot be used after 5 years, then actually after 5 years, if the investor does not gain any profit or saving, they just simply get their money back. So there's no profit or savings obtained if the device only operate for 5 years. Okay, so these are the disadvantages of simple rate of return. Okay, so to evaluate the future value of money, so we say time is money, right? And the amount of money that we have now is not equivalent to the amount of money we have in the future. if we have, let's say, 1,000 ringgit now, in 1 year time, the value of that 1,000 ringgit, if it remains the same amount, the value or the buying power is going to be lower because of inflation. So in order to avoid that, avoid our buying power to reduce, we need to invest, right? We need to invest the money into some channels, some potential options where we can earn more than the amount of inflation. Okay, so we need to utilize this equation. F equals to P 1 plus I to the power of N, where F is the future value, P is the present value, I is the annual interest rate, and N is the number of years. Okay, so let's look at a simple example. Let's say you have 10,000 ringgit to invest and you want to invest for a period of 5 years where you won't touch that money, this money. Okay, so if you invest in an option where you get annual interest of 5%, then after 5 years, the total money that you get is 12,763. If you have another option where the interest you can get is 7% per year, you will get, by the end of the 5th year, you get 14,000. Okay, if you can find an option where you invest and you can get interest of 10% per year, you're going to get 16,000. And if you are lucky enough to find an investment option of 15%, then by the end of 5 years, you can double your money from 10,000 to 20,000. Okay, so that is the idea behind annual interest rate or annual dividend rate, and this is the basis of how we determine where we put our money. Okay, so on the opposite side, we also want to know what is the future value of money equivalent to our current value now, our present value. Okay, so we simply modify the equation to get the present value if we have the future value. So we divide the future value with the same equation, but now we replace I with the letter D. So I previously was interest rate, now D is discount rate. So discount rate can be considered as the interest earned from the best alternative investment option. What does this mean? We'll see in the next few slides. But basically, if we have a higher discount rate, then we have a lower present value. Okay, so what does that mean? Now let's use the same example as we had just now, but let's pretend that we want to know what is the value of 10,000 ringgit in 5 years' time equivalent to now. Okay, so if we put this discount rate 5, 7, 10 and 15%, we will get this following value. Now let's examine. For example, if we have discount rate 5%, then the amount of 10,000 ringgit if in 5 years time is equivalent to 7,835 ringgit now. Okay, in other words, if you invest 7,835 ringgit now in a place where you get annual interest of 5%, then after 5 years you'll get 10,000. Okay, so you see the pattern here. As the discount rate increases, your present value decreases. Now, how do you apply this concept for determining your investment? So let's say you have an investment project that saves 1,000 ringgit in the 5th year, right? The econ example just now. So on the other hand, you have an alternative investment that you can earn 10% of interest per year. So we put in the equation the present value, what would be the present value? If the future value, you can save 1,000, and the next best alternative investment is at 10%. So you get, in this case, 620 ringgit 92 cent. This is the present value. Okay, so this basically means it's neutral between having 620 ringgit 92 cents today or 1,000 ringgit in the 5th year. So this is the balance between having it now or in 5 years time. So in other words, if I need to spend less than 620 ringgit now, I should proceed with this investment project because I would earn more saving than is expected. However, if I need to spend more than 622 now, in order to get the saving 1,000 ringgit in the 5th year, then I should put the money in the alternative investment. That is what is meant. So we can replace with like actual values. For example, let's say I need to spend 700 ringgit. If I put it in this investment project, after 5 years, I will get 1,000 ringgit savings. But if I put 700 ringgit in the alternative investment, if you calculate using the equation just now, the equation for the present value here, the future value here, you put it 700 ringgit and you put at 10%, then you're going to get more than 1,000. So better you put your money in your alternative investment. Okay. So next we go for the term of present value function. So present value function is an accumulation of the discount rates based on the number of years. Okay, so do not confuse the PV used here with the PV for photovoltaic systems. So in economics, PV represents present value. So when we modify this equation, we can get a present value function, which is represented in this form, where D is the discount rate and N is the number of years. Okay. So next we look at the life cycle cost. So the present value of all costs, present and future, for a project is called the life cycle cost of the system under consideration. And it is used to compare investment options. Okay, and the difference between the investment options is called the net present value of the lower cost alternative. Now, what does this jargon mean? Better for us to look at the example. Okay, let's say you are an engineer in a factory and you have two options of buying motors. You want to buy a 100 horsepower motor and you have the option of buying either a good motor or a premium motor. So a premium motor costs $500 more but draws less power. It needs less power to run. Okay, now let's say the motor runs about 1,600 hours per year, and let's say the electricity cost is 8 cents per kilowatt hour. And you want to find what is the net present value of the cheaper alternative over a 20-year lifetime. We assume the motor will last at least 20 years. So should you buy the premium motor or should you buy the good motor? Okay, so we assume a discount rate of 10%. So let's look at the answer. So the good motor, it will draw 79 kilowatts. Okay, and the amount of operation, hour of operation is 1,600 hours. So each kilowatt hour that it uses, it will cost 8 cents. So for 1 year, the total is 10,112. Now for the premium motor, it only draws 77.5. When we multiply using the same values, we get 9,920 per year. So already we can see that even though we need to put initial cost for the premium motor higher than the good motor, the price or the bill for the electricity for premium is already savings. If you minus 10,112 minus with 9,920, you'll get $192 of saving per year by using the premium motor. Okay, so even if we calculate roughly now, we should get uh, if we multiply 192 with if we divide 500 with 192 by right, we should get our money back within 3 years. Anyway, so notice how the annual energy cost for a motor is far more than the initial cost. So now we calculate the present value function. So we assume that it's going to be 20 year and 10% discount rate. So we plug in the values and we get 8.5136 year. Okay, so this is the equivalent present value function for 20 years time and 10% discount rate. So now we multiply. First, we have 2,400 plus, okay, we take the present value function of 8.5 years times 10,000 per year. So this is the value that we are going to get, 88,489. While for premium, okay, we need to pay extra, but then when we multiply 8.5 years times 9,920 per year, we get 87,354. So the net present value, just now when we talk about net present value, the definition is what? The definition is the difference between investment option of the lower cost alternative. So now the lower cost alternative is the premium one. And the difference is obtained by subtracting the value. This one minus this one. So we get 1,135. Now this is what is meant by the net present value. Okay. So this is the difference between the two options. This is the difference if we choose the lower cost option. This is what we call net present value. Okay. So this is the mathematical representation of how we calculate the net present value. Another term that you can use is what we call as internal rate of return. So internal rate of return, IRR, is also known as discounted cash flow rate of return. And it is used to compare investment options. Okay, so if you get the net present value equals to 0, then it is neutral. So that means if it's 0, then either you choose A or B, then you get the same return. Right? For example, if we take the motor example here, if when we calculate good and premium, we get the same amount. Then when we subtract, the value is 0. That means it doesn't matter whether we choose good or premium, you're going to get the same present value, the same rate of return. Now, when we look back, so internal rate of return is the discount rate that makes the net present value equal to 0. So we can use the internal rate of return to determine which option is the best for us. Okay, let's go back to the aircon example. So we have, if you want to buy an aircon, it costs extra 1,000 but saves 200 per year. Simple payback period is 5 years. So determine the internal rate of return for 10 years operating lifetime and for 20 years operating lifetime. So to calculate this, it's simpler for us to use a table. Okay, the table, if any question on economics comes out, then this table you can use to determine the internal rate of return. Okay, so let's look. For example, 10 years, right? We want to compare 10 years and 20 years of operating lifetime. So what we do is we go to the 10-year row and we move up until we reach. Now the number here represent the years. So this one is 6.42 years, 5.89 years, and as we move along the horizontal line, we find this is closest to 5 years, 5.02. So when we refer back to the top column, the label column here, we find the value as 15%. So we can say that the sentence is already given here. For example, a 10-year project with a 5-year payback period has an internal rate of return of just over 15%. Right? So if we go for 20% or 20 years lifetime, and we follow the horizontal row until we reach 5 years, then the value we find is somewhere between this one. This is 5.1 years, this is 4.66 years, so we can extrapolate. But we can roughly say that the internal rate of return is around 20%. So we can conclude here that if the operating lifetime is longer, then we can have better internal rate of return. Right? From just now, 10 years to 20 years, so we can improve our internal rate of return by about from 15 to around 20%, so about 5%. Okay. So by logic, you can already determine from the graph here that if the project has a longer lifetime, then it's going to provide you with a higher internal rate of return. Right? Okay. So when when the lifetime greatly exceeds the simple payback, like the lifetime goes beyond 20 years or more, then the internal rate of return approaches the initial rate of return. So we have this, the gray line here represents the rate of return if the air conditioning, for example, lasts forever, which is of course impossible. But as you can see, the longer the product, or the example air conditioning, right? The longer the air conditioning lasts, then the closer that you're going to get to your initial rate of return, which is good. Okay, since it's common for the simple payback period to be used to judge a project and it's often misleading, so we can possibly use the internal rate of return to translate the payback into a more convincing argument. Okay. Okay, when we talk about investment, usually it involves loans. And when we talk about loans, usually you need to pay back the loans either monthly or annually. So it is important for us to annualize the investment in terms of yearly, every year. Okay. When we want to invest in something, or when a company want to invest in a project, typically they will apply for bank loans. Okay, and bank loans require you to pay either annually or monthly with a specific amount of interest. So we need to factor in the interest as well in our calculation to determine whether our investment is worth it. Okay, so from present value function, it can be thought of as a principal borrowed money. So we go back to the equation here. So we have the present value and we have the annual payments and we have the present value function where it's dependent on the discount rate and the number of years. So we need to know if we are charged a certain amount of interest rate per year from our bank loan, how much do we need to pay off the loan in each year? So how do we determine whether the amount of profit that we need based on the amount of loan that we need to pay for each year. Okay, so to do that, we need to calculate the capital recovery factor. And the capital recovery factor is actually the inverse of the present value function. Okay, you see this one is swapped to the top, this one goes to the bottom, and again we replace the discount rate with the interest rate. This is called the capital recovery factor. Okay, so for simplicity, we usually use a table. So the table here, so we have this value here represent the interest rate, and this value here represents the loan term, the duration of the loan. Okay, so let's look at an example. Let's say we have a 3 kilowatt PV system. The capacity factor is 0.25 and the cost to install is 10,000. This is an old example when the price of PV is still expensive. Okay, so no annual cost associated with the system other than the payments. So the loan is a 20-year loan and the interest rate is 6%. So we need to find the cost of electricity generated by the system. So how do we do this? So first we calculate the amount of annual payment that we need to pay each year throughout the 20-year period. Okay, so we have the present value 10,000 and capital recovery factor 0.06 and 20. So we have the value 0.0872. Where do we get this value? We get it from the previous table. So the year is 20-year loan and the interest rate is 6%. So we get the value of this one, 0.0872. So we put in this value in the equation, 0.0872 times 10,000. So each year we need to pay $872 for 20 years. Okay, now to find the annual electricity generated, we recall the definition of the capacity factor as the rated power times the total of hour per year and times the capacity factor. So the rated power is 3 kilowatt multiplied by 8,760 hours per year multiplied by the capacity factor, which is 25%. So we get that the total amount of energy that can be generated from our system is 6,570 kilowatt hour per year. So now we calculate the cost. We need to pay $872 per year. And the amount of energy we can generate is 6,570 kilowatt hour per year. So when we divide, what will happen? We will get a value of 13.3 cents per kilowatt hour. This is the cost of our electricity from PV. So this value we can use to determine whether the project is good or not. If let's say we can sell to TNB the PV that we generate at a price that is higher than 13.3 cents. Let's say we can negotiate with TNB and TNB agrees to buy from us at a cost of, let's say, 20 cents per kilowatt hour. Then by right, we can invest in this project. But let's say TNB only wants to buy from us 10 cents per kilowatt hour of energy we generate. Then what happens is we need to sell below our cost. So that makes the project not feasible. So this value here, the value of money that is equivalent to the amount of energy generated is what we are going to cover in our last concept for this video, which is the levelized cost of energy. So levelized cost of energy, abbreviation LCOE, measures the lifetime cost divided by the total energy production. Okay, so lifetime cost dollar divided by energy production kilowatt hour. So dollar per kilowatt hour. So it calculates the present value of the total cost of building and operating a power plant over an assumed lifetime. So since we only consider the dollar per kilowatt hour, it allows us to compare between different technologies and technologies that has unequal lifespan. Like maybe solar 25 years, maybe diesel generator maybe only 5 years. But since we only calculate dollar per kilowatt hour, then we can calculate the actual value that can be provided. Okay, regardless of the lifespan, project size, capital cost, whatever, we are only concerned with the cost per kilowatt hour generated. Okay, so the simple LCOE concept is when we have an energy system. These are the costs, right? The cost here, we have initial cost, the cost to set up the system, and the annual expenses for maintenance, for operation, for whatever. And we get, let's say, the annual cost per year is 125. Okay, this is example for solar. Now, let's say for the site where we install the solar, we have annual energy production of 1000 kilowatt hour. So the cost is 125 per year and the total energy is 1000 kilowatt hour per year. So we simply divide 125 divide by 1000 and we get $0.125 per kilowatt hour or 12.5 cents per kilowatt hour. So we do the same for other types of energy sources. For example, wind or 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 conventional generation like fossil fuels, and we divide the total cost per year with the annual energy production, and we compare which one has the lowest cost per kilowatt hour, then that is our choice, because that's the most economic choice. Of course, when we consider other factors like environmental effect, then other types of consideration comes into play. But when we talking about purely dollars and cents, then the cheaper option, cost per kilowatt hour, should be our choice. Okay, so let's see example for a solar farm. A solar farm has, let's say this is a straightforward example. We have 4,000 panels, each panel rated at 250 watt peak. So the capital cost is 5 million. Operating and maintenance cost is 50,000 per year. Okay, the project will be financed $4 million from a 20-year loan at 7% interest rate. And then equity investment, 1 million, that needs a 15% annual return. So equity investment is basically you ask people to invest and you promise them a return of 15% per year. Okay, so capitalists, capital venture companies, okay, they invest in your company and you need to provide them with 15% annual return. Okay, so the solar farm is expected to receive this amount of irradiation and a performance ratio of 80%. So assume no annual degradation, what will be the LCOE value to make the project viable? So this is the calculation. So annual energy, when we calculate, capacity 1000 kilowatt or 1 megawatt times 1700 hour, this is the peak sun hour value, times the capacity factor or the performance ratio 0.8. So we get this is the amount of energy we can generate a year. So annual cost is the loan prepayment plus equity investment plus operation and maintenance. So loan repayment is $4 million times 0.0944. Well, how do we get 0.0944? Again, we refer to the table. So 20-year loan at 7%. So 20-year loan at 7%, we get 0.0944. So we plug in the values in the equation, we get 377,600 per year. This is the amount of annual loan repayment you need to do to the bank. And return for equity investment, 0.15, 15% times 1 million. So you need to provide return to your investor, equity investor, 150,000 per year. Okay. So the operation and maintenance is 50,000. Going back to the question, operation and maintenance is 50,000 per year. So 50,000 plus equity investment 150, so 200,000. 200,000 plus loan repayment, this value here, so you get 577,600. You divide by the annual cost with the annual energy generation to get this value here, 42.47 cents per kilowatt hour. So this is your levelized cost of energy. In other words, if you can sell the energy you generate higher than this value, then you should invest in this project. But if you cannot sell higher than this value, then you should not proceed with the project because you will incur a loss. So this is the idea behind calculation of the levelized cost of energy.